Oh, welcome to another edition of Physics, the redo of physics lectures by Professor Lewin. Just adding context, perspective maybe, different way of looking at it. I think a better way. More focus on cause, less focus on I'm trying to get a job doing math for whatever architectural firm. Yes, I mean, our people have to learn stuff to be practical. And then there's the subject of physics itself, which I think is undertaught in universities. So they teach people how to do mechanics, how to make a car. They don't teach people how to understand, or they don't have any, there's no subject. Why is this stuff happening? That's not really a subject for these people. So anyway, that's the part I'm going to add. And such. So leave us continue. Lecture 7, Capacitance. Interesting subject.
When I assemble charges, I have to do work. We discussed that earlier. And we call that electrostatic potential energy.
I don't know why they call it that. It's voltage. So that's what it comes down to in a sense. You've got to overcome pressure. And you're pressurizing a system. And what else can you say? The energy goes somewhere. Yeah.
Today I will look at this energy concept in a different way. And I will evaluate the energy in terms of the electric field. Suppose I have two parallel plates, and I charge this one with positive charge, which is the surface charge density times the area of the plate, and this one negative charge, which is the surface charge density negative times.
So it's just pointing out that they'll hold so much charge. There's a certain amount of area, you put the charge on the surface, it'll spread out over the surface. The more charge you put on, the higher the density of the little charged bits. Okay, so just think of it as a bunch of little things, little balls. You're putting them on a surface, and they don't like each other, so they repel, and they just keep getting closer and closer to each other as you pile more and more on. And you have to do work to pile more on. At a certain point, it becomes real work. Oh, sorry, monitor trouble again. Stop being a pain in the ass, please. No, it doesn't want to stop. Alright, I'll just break the switch off. Alright, we'll break it yet. Break it tomorrow.
Area of the plate. And let's assume that the separation between these two is h, and so we have an electric field, which is approximately constant. And the electric field here is sigma divided by epsilon 0. And now I'm going to take the upper plate and I'm going to move it up. And so as I do that, I have to apply a force.
So no different really than pulling two magnets apart that are attracting. So you're pulling the magnets apart. So that's the work component. You have to do work. And in this case, the work has a consequence. The magnets can't change who they are because of the work you do. So, but these things can. They can adapt to the work.
Because these two plates attract each other, so I have to do work. And as I move this up, and I will move it up over a distance x, I am creating here electric field that wasn't there before. And the electric field that I'm creating has exactly the same strength as this, because the charge on the plates is not changing when I'm moving, the surface charge density is not changing. All I do is I increase the distance. And so I am creating electric field in here.
Something the way, that's not exactly the way I would look at it. What you're doing is moving the things that are attracted to each other further apart. And that's sort of, you would, kind of obviously those little bits are attracted to the other little bits, and they're repelled by each other. And so what's the consequence of when you move them closer or whether you move them further apart? And I would argue a sensible notion is that you're moving them apart, that they're going to take advantage of that space, the atmosphere, and be compelled to move down towards to bulge a little. So if they were on the surface and they were halfway in the surface, you could think in like a layer of water, and they're just bobbing in the water, you could think of it as them floating a little higher because they're attracted to the thing on the other side. And so if they move up, then you can understand how they can get closer together because some of them are in different heights. So when they were all on a flat plane, they could only be a certain distance from each other, pressure-wise. And as they move up, they kind of can depressurize. So you can sort of understand that if you move the plates closer and closer together, the attraction is getting stronger and stronger between the charges. And so they're both kind of moving up, and that moving up is allowing there to be more space between them, which is lowering the pressure. So you're creating more space for them to occupy, essentially. So the closer you get the two plates, and the more they're going into another dimension of space, so they're not stuck on a flat plane anymore, they're bulging up a little bit, you can sort of understand that that creates more space for them to occupy, which means their voltage would be lower. So the further apart the plates you move them, the more they're sticking to the plate now instead. So they're on a flatter surface, and therefore the pressure goes up because they don't have that extra space anymore. Didn't do a perfect job of that, but I'm just, you haven't created more. This field stuff doesn't matter. The only thing that matters is the relationship between the little bits on one plate and the little bits on the other plate. Obviously the force transmitted between them matters, but I'm just saying when you have plates that are close, you're not really affecting well, you are affecting, but I'm just saying you're not you don't need to think of it as creating space. You have to think about what the distance means to the charges, and the distance means there's less attraction between them, and if there's less attraction, there's less ability for them to float higher in the water.
And for that I have to do work. That's another way of looking at it. How much work do I have to do? What is the work that Walter Lewin has to do in moving this plate over a distance x? Well, that is the force that I have to apply over that distance x. The force is constant, and so I can simply multiply the force times the distance. That will give me work.
So it's all going to interpret in a sense to back to watts somehow. That's what I would do with it. And you're putting a certain amount of, you're adding a certain amount of capacity to the voltage, but at the same time well, that's as far as we'll go. So you're just going to increase the voltage, which is going to increase the potential of those plates to produce work, because you've added this extra work. The work went into the system. The system is can't make more charges. So if it can't make more charges, the only thing you can really do is make the charges more, give them more pressure, give them less pressure. So if you do positive work, that is you do, well, negative work, that is you got a free ride. The free ride is because you diminish the voltage of the system. And if you increase the voltage of the system, you've given it more capacity to do work. And that was the work you did to pull the plates apart. Not perfectly eloquent again, but close enough.
And so the question now is, what is the force that I have to apply to move this plate up? And your first guess would be that the force would be the charge on the plate times the electric field strength. A complete reasonable guess, because you would argue, well, if we have an electric field E and we bring a charge Q in there, then the electric force is Q times E. I have to overcome that force, so my force is Q times E. Yes, that holds most of it.
Well, the problem with that logic is obviously if with each step you move it, you're changing the amount of work you're doing. It's getting easier to move them apart the further away you go. So, because you're going to eventually destroy the adhesion between them altogether as you're increasing that voltage. Yes. And what else needs to be said about that? Yeah, so it's going to be less than an equal amount. It's not going to be proportional. So, yeah.
Time. but not in this case. It's a little bit more subtle. Let me take this plate here and enlarge that plate. So here is the plate. So you see the thickness of the plate now. This is one plate. We all agree that the plus charge is at the surface. Well, but of course it has to be in the plate. And so there is here this layer of charge Q, which is at the bottom of the plate. And the thickness of that layer may only be one atomic thickness, but it's not zero. And on this side of the plate is that electric field, which is sigma divided by epsilon 0. But inside the plate, which is a conductor, the electric field is 0. And therefore, the electric field is, in this charge Q, is the average between the two. And so the force on this charge in this layer is not Q times E, but is 1/2 Q times E. So I take the average between these E fields, and this E field is then this value.
I think that's all kind of just arbitrary. What's really happening is that pink layer he drew, the layer of the charge, is getting thicker. As I'm pointing out, the charge is, as you're low, it's getting thinner in this circumstance. The charges had more space to occupy when the plates were closer. So the closer the plates, the thicker that layer of pink gets. The further away you put them, the thinner it gets. And as it gets thinner, the same amount of charge has to be in a smaller area, which means the voltage has to go up. The pressure between them has to go up.
And so now I can calculate the work that I have to do. The work that I have to do is now my force, which is 1/2 Q times E, and I move that over a distance x.
Maybe I'll do a quick drawing here just to make sure I'm understood to some extent. Yeah, some kind of getting somewhere. So what we're really talking about, they're talking about one thing, I'm talking about another thing. So that's part of the problem here. But you have these little charge bits. So then they're on a surface. And so the point would be is when the surfaces are when two surfaces are close, you know, and these things are attracted to each other as they're opposites. The point would be is this strength of this pull is very strong because they're very close. So it's an inverse square thing. So the closer they get, the stronger the force between them is. And so you know, the trick is that these atoms are really small. So for the ones in the middle, there's not going to be any inverse square law. So it kind of is an average over the whole plate that you get an inverse square law, but you really don't between these two plates when they start getting close. It's even stronger than the inverse. It diminishes it with distance, but it doesn't mean much when the plates are close. I'll say that. So if I move the plates further away, the point is that, you know, these other charges, let's just say there's charges here, so they're separated by a distance. And now when I move the plates apart, these charges that were sticking out are now going to have to go back on that line. And so that's going to mean the distance between these is going to have to be closer. You can sort of see. So that these charges and these charges are all going to be closer to each other. And that means, just by the simple point that I'm arguing, that electrons, the pressure is in between the electrons. The reflections of the electromagnetic radiation. So the electromagnetic radiation, the little photon bits, the little force bits, bounce between the electrons. They're creating the pressure. So the closer they are, the more bounces you get. The further away they are, the less bounces. So anything that forces them closer together is going to create more pressure between them. And anything that allows them to separate, create more space to occupy, will reduce their pressure. So as you bring the plates together, the voltage goes down. As you bring the plates apart, the voltage goes up. So the pressure goes up as you force them to live on the same plane. I feel better about that. Yes, I think that's a better explanation. to the video.
And so what I can do now is replace Q by sigma A. So I get 1/2 sigma A times E times X. And I multiply upstairs and downstairs by epsilon 0. So that's multiplied by 1. And the reason why I do that is because then I get another sigma divided by epsilon 0 here, divided by epsilon 0, and that is E. And therefore, I now have that the total work that I, Walter Lewin, has to do is 1/2 epsilon 0 E squared times A times X. And look at this. AX is the new volume that I have created. It is the new volume in which I have created electric field. And this now...
So just to understand, this equation is fine, but I'm just saying it's using a different a measure of something that are proportional. So the space you're creating is going to be proportional to the space being contracted by the electrons. So the electrons, the ions, let's call them, they're not electrons, they're atoms, and they're ionized. So you either have positive ions or negative ions, in my opinion. That's what's really happening here. So the ions are the amount they compress back onto the straight line is proportional to the amount of that extra space he made. So essentially you could replace this math with the same, just use a different constant, and you've got the same equation, just measuring the extra space lost. The extra space the ions have to exist in. They're existing in less space.
Calls for a work done by Walter Lewin per unit volume, and that now equals 1/2 epsilon 0 times E squared. This is the work that I have done per unit volume. And since this work created electric field, we call it field energy density. And it is in joules per cubic meter. And it can be shown that in general, the electric field energy density is 1/2 epsilon 0 E squared, not only for this particular charge configuration, but for any charge configuration. And so
he did use the word in general, so conceding these are approximations.
Now we have a new way of looking at the energy that it takes to assemble charges. Earlier we calculated the work that we have to do to put the charges in place. Now, if it is more convenient, we could calculate that the energy, electrostatic potential energy.
So again, this potential energy is just really in the form of pressure. And so you're just saying, how compressed are the bits, and then how many bits do you have? And that's all there is really here. There's only two components. There's the pressure, and then there's the number of things under pressure.
Is the integral of 1/2 epsilon 0 E squared over all space. If necessary, you have to go all the way down to infinity. And here I have now dV. This is volume. This has nothing to do with potential, this V. In physics, we often run out of symbols. V is sometimes potential. In this case, it is volume.
So, all you can say is, well, you ought to come up with some better way of doing it then, if that's just kind of retarded. You shouldn't be using this. You could put a line through it. You could make something, some other hieroglyphic connotations, volume. You could just put a circle around the V, make a small V with a circle around it, volume.
The only reason why I chose H there is I already have a D here, so I didn't want two Ds. Normally we take D as the separation between plates. And so this now is another way of looking at electrostatic potential energy. We look at it now only from the point of view of all the energy being in the electric field, and we no longer think of it perhaps as the work that you have done to assemble these charges. I will demonstrate later today that as I separate the two plates from these charged planes, that indeed I have to do work. I will convince you that by creating electric fields, that indeed I will be doing work. So from now on,
he'll put energy into the system. So, yeah, I mean, distance in this case, because it's attraction, distance is going to create pressure. If it was repulsion, it would be the other way around. It's more easily understood when you're pushing things together how you're making pressure. But when you're pulling things that are attracted apart, you're also making pressure.
We have the choice. If you want to calculate what the electrostatic potential energy is, you either calculate the work that you have to do to bring all these charges in place, or if it is easier, you can take the electric field everywhere in space, if you know that, and do an integration over all space. We could do that, for instance, for these two parallel plates now, and we can ask what is now the total energy in the field. And at home, I would advise you to do that the way that is done in your book, whereby you actually assemble the charges minus Q at the bottom and plus Q at the top, and you calculate how much work you have to do. That's one approach. I will now choose the other approach, and that is by simply saying that the total energy in the field of these plane parallel plates is the integral of 1/2 epsilon 0 E squared over the entire volume of these two plates. And since the electric field is outside zero everywhere, it's a very easy integral. Because I know the volume that I have, if the separation is h, so we still have them h apart, this volume that I have is simply A times h, and the electric field is constant, and so I get here that this is 1/2.
So he's still just talking about the part he added. He's not talking about the entire system.
Epsilon 0. For E, if I want to, I can write sigma divided by epsilon 0. I can square that. And dV, in doing the integral over all space, means simply I get A times h. It is the volume of that box, so I get A times h. And so this is now the total energy that I have. I lose one epsilon here. I have an epsilon 0 squared and I have an epsilon. I also remember that the charge Q on the plate is A times sigma, and that the potential difference V, this now is not volume, it's the potential difference between the plates, is the electric field times h. The electric field is constant. I go from one plate to the other. The integral E dot dl, in going from one plate to the other, gives me the potential difference. And so I can substitute that now in here. I can take for A sigma, I can put in the Q, and you can also show that this is 1/2 QV. V being now the potential difference between the plates. And so this is a rather fast way that you can calculate what the total energy is in the field, or say the same thing, the total work you have to do to assemble these.
Sorry, that was just way too sloppy. I mean, the U started off equaling something, and then it ended up being the V equaling something, which just doesn't, sorry. Didn't sit right with me.
Charges, or to say it differently, the total work you have to do to create electric fields. You have created electric fields that were not there before. I now will introduce something that we haven't had.
Let's understand, the electric field is just what the electrons are going to reflect back and forth to each other, essentially. So the electron's a little body. It's gravity goes in mixed, red, black, red, black, red, black. It produces black. Okay. And the red also comes out, but it comes out perpendicularly. So if it's ever hit by red, that red doesn't go where it was going, it comes out perpendicularly. But that's really the only difference. But the important part is the black is always reflecting. And so all of this electrical stuff just has to do with electrons, essentially, and the fact that they're reflecting the energy that comes at them. And that's what makes them repulsive, kind of obviously.
Before, and that is the word capacitance. I will define the capacitance of an object to be the charge of that object divided by the potential of that object. And so the unit is coulombs per volt. This V is volt now, it's potential. But we never say that it is coulombs per volt in physics. We write for that.
So again, volt isn't potential, it's pressure. The pressure is obviously creates potential. So when an atom has pressure, it's waiting to pressurize something else. It's waiting to share that. So it's potential, but it's real thing. It's pressure.
Capital F, which is farad. We call that 1 farad, is the unit of capacitance, undoubtedly called after the great maestro Faraday. We will learn more about Faraday later in this course. So let us go to a sphere which has a radius r.
apparently yeah, it's very nice they use the word, but I mean, it's like with all these things, it's like a Newton is like, 1 Newton is like a nuclear bomb or something, and 1 farad is apparently so much electricity capacity, so much, it's not an infinite plane, but it's like the whole surface of the Earth kind of a thing. It's just kind of, you wonder why it's such a big unit.
And let us calculate what the capacitance is of this sphere. Think of it as being a conductor, and we bring a certain charge Q on this conductor. It will then get a potential V, which we know is Q divided by 4 pi epsilon 0 r. We've seen it many times. And so, by definition, the capacitance now is Q divided by the potential, and therefore this becomes 4 pi epsilon 0 r. So that is the capacitance of a single sphere. And so we can now look at the values as a function of R. I have here some numbers. I calculated it for the Van de Graaff, and I calculated it for the Earth. If you want 1 farad capacitance, that's a real biggie. You need a radius of 9 times 10 to the 9 meters. That's the 4 pi epsilon 0 that comes in there. That's huge. That's 25 times the distance from the Earth to the Moon. That's a big sphere. We have a capacitance of 1 farad.
Right. So that's the distance from the Earth to the Moon is like the diameter of the Sun, or it's even more than that. So kind of silly.
The Earth itself, with a radius of 6,400 kilometers, would have 700 microfarad. The Van de Graaff 30 centimeters radius would be 30 picofarad. The pico is 10 to the minus 12. And if you take a sphere with a radius of 1 centimeter, then you have roughly 1 picofarad, 10 to the minus 12 farad. So this gives you a rough idea about the size of objects and how they connect to their capacitance. So if I bring all these spheres at the same potential, so I charge them all up to the same potential, then the one with the largest capacitance will have the most charge. And that, of course, is where the word capacitance comes from. It is the capability of holding charge for a given electric potential. Don't confuse that with electric fields, because if you bring all these spheres at the same potential, then the one with the strongest electric field, that's the one which has the smallest radius. We discussed that last time. Now,
so, and the radius, again, just has to do with how much separation there is between the repulsive forces. So, let me draw that one just to be, because I already explained it, but I think it's worth just pointing it out what I'm pointing out, because I think it's really important, because I think this is how it works. So the point would be is you have a curved surface, so you can have a tight curve or you can have a very loose curve. And the point would be is if I put little lumps on there, you could sort of see how the little lumps wouldn't be able to communicate very well on the tighter curve as they can on the flatter curve. So the flatter the curve, so if I just put lumps on a straight line, and each lump radiated force in all directions, so like this, okay, you could sort of understand that the ones that are on the curve, a lot of their radiation is going to miss hitting the other guy. So the more curved you are, the more of your radiation can escape. So you can be a lot closer together and have I'm trying to think of the right way to say it, the same pressure. No, you can get more density on the same surface, and the closer you are to a straight line, the less density you can have, because technically these guys can't stay this close, so they end up this far away. So you can only hold a certain number of them. So if you want to increase the capacitance, you want to try to increase how many of these things you can fit for a given voltage. So in a sense, this is just cheating by allowing the force to you can increase the voltage because they can get closer to each other, so they're technically under more pressure, but they're how do you even say it, they're not feeling each other's pressure. So they're excreting the pressure out as if they're 1,000 volts. But the voltage they feel between each other is much lower because they're not feeling each other's force. So they think, since these are all like 1,000 volt pressurized atoms, so the atoms are pressurized to 1,000 volts, but these atoms don't feel the 1,000 volts. They only feel maybe 500 volts or something. So they can get much closer, increasing the density. And yeah, so it's probably not the best way to say it, but the real point is that the surface they're on is, say, 500 volts of pressure. So their averages are that they're this far apart, and at this little lump they're condensed. So the more condensed they are, the closer you get these little things together, the higher the voltage. So the point is any mechanism you can use to get them to move closer to each other will increase their voltage. It'll have to do. I'm sorry. It'll have to do that the drawing wasn't in the right place. But anyway, all right, we'll continue. Attempt to.
I will look at the situation a little bit differently. I have here a sphere, B, positively charged, and I place it close to another sphere, A, which is negatively charged. And so, by my definition, I can say that the capacitance of B is the charge that I have on B divided by the potential of B. That would be my definition. But there is here this object which charge negative. And how did we define potential? Potential was work per unit charge. I go to infinity, I put plus Q in my pocket, I approach B, and the work I have to do per unit charge is the potential of B. That's the definition of potential. But B is repelling me, so I have to do positive work. But A is now attracting me. And so the work I have to do is less the work per unit charge. And so, because of the presence of A, the potential of B goes down, and therefore the capacitance of B goes up. And so now you see that the presence of this charge sphere here has an influence, an important impact on the capacitance of B, and therefore...
All right, to attempt to make that make sense, what is happening, as much as you say a conductor is going to have an even charge around it, the density of the charge won't be even. So what's going to happen when you move A next to B is that there's going to be a higher density of charge right next to A, where A is. The two are going to create a higher density of charge, which is going to be, in my opinion, a higher voltage. Has to be, to some extent. And so you've eliminated some of the repulsiveness of B because you've forced it onto the side that A is on. It's pointing the wrong way, so it's not hitting you.
It is really unfair to call this the capacitance of B. We think of it as the capacitance of B in the presence of A. So it's no longer just B alone. And so I'm now going to change the definition of capacitance. And I'm going to change it in the following way. I have two conductors. And these two conductors have the same charge but different polarities. And now the capacitance of this combination of two conductors is the charge on one of them, which is the same, of course, on the charge of the other, except different polarity, divided by the potential difference. So that now is my new definition of capacitance. So you always deal with two objects, not with one in isolation. If you have the charge on one of the two and you divide it by the potential difference between the two. You may say, well, it's a little artificial to have two conductors and one is positively charged and the other has exactly the same amount of negatively charged. Well, it is not so artificial as you may think. Remember then we had this Winghurst machine which I was cranking and I was charging one plate positive and the other one negative without my doing anything. If one becomes positive, the other one becomes negative by exactly the same amount because you cannot create charge out of nothing. So if you charge one thing positive, chances are that something else
All right, well, that's really not true. So the obvious example would be is if you're making single charges, like a balloons or something, you're going to charge one positive and one negative. It's very unlikely that you're going to end up with the same charge on both of them unless you use some kind of machine where you're putting both the positive and the negative electrode to the machine. So the machine is conservative. It's making just as much negative as positive. When the Venn diagram creates a positive at the top, it's also shoving a ton of negative into the bottom, I mean into ground. So it's making an even number. So the creation is even, but how you distribute it can be very uneven. So in some sense, look, it's fine. I don't, why would I want him to do more complex mathematics? So I'm glad that he's saying they're the same charge. But I think in most circumstances, you're not going to have the same charge on two surfaces.
Is charged negative by the same amount, but with opposite polarity. So it's not so artificial that you have two conductors with the same charge, but opposite polarities. So now, we have two conductors there. So if we go to these two parallel plates, the question now is, what is now the capacitance then, according to our new definition of these parallel plates? Well, that capacitance C is the charge on one plate divided by the potential difference between the two plates. And the charge on one plate is sigma A. And the potential difference between the plates is the integral of E dot dl. They are separated there by a distance h. I will change that now to a d, because that's more commonly done, that the separation between plates is d. There was a reason why I didn't want to put a d there, because I didn't want to get you confused, but now there is no confusion. And so the potential difference is the electric field between the plates times the distance d. But E itself is sigma divided by epsilon 0.
So again, the distance between the plates is the important part, obviously. But what it's changing, as you decrease the distance, you're increasing the amount of volume that the charge is occupying, because the charges are moving towards, and in the case of repulsive plates, moving away. So they're increasing their two-dimensional space. So they go from a one-dimensional line, you could say, to a two-dimensional space, and that increases the volume they can occupy.
So we get here sigma divided by epsilon 0 divided by d. I lose my sigma, and so two parallel plates have this as the capacitance. It's linearly proportional with the area of the plates. That's intuitive.
So when Ken Wheeler says something like, less is more capacitance or something, he's, it's true in the sense that when you reduce the space between two plates, you increase the capacitance. But you're not really increasing you're not mechanically producing space. You're just doing the proximity space of and you're also creating the problem of your voltage has to go down. Because if your voltage doesn't go down, the particles will just jump across.
Pleasing. The larger the plate, the more charge you can put on there. And it's inversely proportional with the distance between the plates. The smaller you make the distance, the larger is the capacitance. Well, that goes back to this idea, that the closer A is to B, the larger effect that will have on the capacitance. And if you bring them very close together, this potential will go down and so the capacitance will go up. So it's not too surprising that you see D here downstairs. The closer you bring the plates together, the higher the capacitance will be.
So in that two-circle argument, you can almost think of the two circles getting fatter on one side, creating more space for the charges to occupy, and so therefore they have more real estate on the other side. So it's just creating more real estate, and when you create more, and that increases the fact that you can put more charge on because you made more free space for the charges.
Let us look at some numbers. Suppose I have a plate, very large, 25 meters long and 5 centimeters wide. 25 meters long and 5 centimeters wide. I have two of them, called a plate capacitor. And let the distance between them, d, let d be, let's make it very small, because we want a real big capacitor, 0.01 millimeters. Very small gap between them. So now I substitute the numbers in there. I can calculate the area. I can calculate the area here, the plate, in square meters, of course. Multiply by epsilon 0 and divide it by d in meters. And when you do that, you find that the capacitance of this big monster is only 1 microfarad. It's not very much. And when you go to Radio Shack and you buy yourself a 1 microfarad capacitor, you don't buy something that is 25 meters long and yay big. Well,
part of that is because the closer you make them, then the more you have to limit the voltage. The voltage can't go very high. But yeah, I don't know exactly how they how capacitance isn't affected by voltage. But whatever. Continuing.
Well, you may actually buy that without you realizing that, because these large plates, these very long ribbons of conductors, two very close together, separated by some insulating material, very thin, they are rolled up often. And you don't notice that, but they are rolled up and they're put in a little canister, and that then gives you a parallel plate capacitor. I brought one with me. That is one that I have used for several years, but today I decided to cut it open for you so that you can look inside, and then you actually will see the, you're going to see it there. This is the canister in which it was. And so I cut the canister open, and when you look here, you see there is this conductor, looks like aluminum foil, and then there's insulating material, and then you find more conductors on the other side. And so it's rolled up. Here, if I unroll it here, I'm breaking it, but that's okay. So you see the idea of a parallel plate capacitor, how it can be rolled up nicely.
It's kind of a crappy insulator, the paper type. It's just really to keep the two pieces of foil from hitting each other, so it's not even really an insulator. It's just something to prevent the two pieces of foil from hitting each other. And so if you use oil or something else that's a better insulator, works better.
And you're not realizing that you're really talking often about meters, many meters of material. Now, through chemical techniques, the distance d can easily be made 1,000 times smaller than this. And if the distance is 1,000 times smaller, then you would get a capacitance of 1,000 microfarad.
So they put a film of, lacquer or something over the metal, so then they can get them really close.
Compare that with the Earth, which is only 700 microfarads. So a capacitor like this, 1,000 microfarad. If we bring the potential difference over here, then we get a tremendous amount of charge on here. In fact, if I hold this in my hands, and if I assume that the potential difference between my left hand and my right hand is 10 millivolts, then I would bring on this capacitor 10 microcoulomb. That is a tremendous amount of charge. In fact, 10 microcoulomb is the maximum charge we can ever put on the big Van de Graaff. We calculated that last time. If we put more on the Van de Graaff, it goes into discharge.
So he's basically saying it might go in slow, it might take a while to charge, but it'll charge to a lot of density, but at that very low voltage. So it's ions that aren't very pressurized. They're low pressure ions, very low pressure. So they can be close together.
And by simply holding this in my hands, I could put 10 microcoulomb here on this capacitor. Now you may say, well, yeah, but the potential difference between your right hand and your left hand, 10 millivolts, isn't that funny? No, not really. In the future, I will give a lecture and then discuss electrocardiograms, and you will see then that there is a potential difference between the left side of your body and the right side, which is several millivolts. So it's not as artificial as you may think. Actually, we'll take a cardiogram in class, and you can see it really working.
Well, but the point would be, though, is those millivolts aren't going to be able to do any real work unless you up that voltage.
How much energy can I store in a capacitor? Well, we already calculated that. We had the energy. This was the plate capacitor, 1/2 QV, and we can now substitute for we can substitute in there the capacitance C, and the C is Q divided by V, and so this is also 1/2 C V squared. That's one and the same thing. So either you take the charge on the capacitor multiplied by V, or you take the capacitance multiplied by the V squared. The capacitance is never a function of the charge that is on the object. Here, if you look here, the capacitance is only a matter of geometry. And when you look there, the plate capacitor is only a matter of geometry. Never does the charge show up in there. So I mentioned that I can bring 10 micro Coulomb on this capacitor, and yet on the Venn diagram I can also only bring 10 microcoulomb. That's the maximum I can do before it goes into breakdown. We can think of a capacitor as a device.
Okay, so the Venn diagram is obviously putting very high voltage ions on the Venn diagram, so they have to be far apart because they're high pressure. So that's the idea. So even though it has this nice surface, it can't hold too much in terms of actual ions. So the number of sponges, or whatever you want to call it, you could think of the atoms as little sponges, and you say they hold so much. So you've put a good amount of water in the sponges. So when he was doing the micro Coulomb, that was like sponges where you just put one little drop in each little sponge, tiny bit of it's probably not the best. It doesn't give you the repulsion idea. But anyway, it doesn't have much density. You can't squeeze much out because it's might be a lot of water, but there's only 10 sponges. Where you can have another circumstance where you have 1,000 sponges with a little bit of water. That's trying to come up with an analogy between the two being the same amount of watts, so to speak.
That can store electric energy. I will now return to my promise that I was going to demonstrate to you that I have to do positive work when I create electric fields. In other words, when I take these two charged plates and I bring them further away from each other, then I do positive work. And how am I going to show that to you? I have two parallel plates. They're on the table there. You're going to see them shortly projected there. And we have here a current meter. I put an A in there for amperes, symbolic. Current meter. And I'm going to have a power supply and put a potential difference over here. This is the capacitance C we normally use for a capacitor, symbol of two parallel lines. I'm going to put a potential difference V over the capacitor of 1,000 volts. So let me put a delta here to remind you that it's the difference between the two plates. As I do that, as I connect the power supply to these two ends, charge will flow on here, and so you will see a very short surge of current. So the amp meter will give you only for the short amount of time that I'm charging, will show you that there is charge flowing, and you will see that. But that's not...
Well, somewhere in here he has to have a voltmeter, so I guess I'll draw that next.
Really the goal of my demonstration. What I'm now going to do is I'm now going to increase the separation, the distance d, of these two plates. And remember that the potential difference over the plates, which I call now a capacitor, is the electric field times the distance, and the electric field is constant. If I charge the capacitor up with a certain charge, there is plus Q here, there's minus Q there, and then I remove the power supply, it's no longer there, that charge is trapped. That charge can never change. And so if the charge doesn't change, the charge surface density doesn't change, and so the electric field inside remains constant.
So it's very deceptive, these words, charge and field densities and all this kind of stuff, because really there's only two components. There's the number of ions, the number of atoms that are pressurized, and their amount of pressure. Those are the only two factors here.
So exactly what we did there. And now I'm going to move them further apart. Therefore, I'm going to make D larger, and that can only happen if the potential difference between the plates increases. And I will start off with 1,000 volts, whereby D is 1 millimeter, and then I will open up this gap up to 10 millimeters. And then I have a potential difference of 10,000 volts. But since the energy in the capacitor...
So it seems, a 1-to-1 ratio. So every millimeter he moves, he increases it by twice as much. So I don't know what the half is for, because it's really a doubling of the voltage, but whatever.
Is 1/2 Q times the potential difference V. This V is the same as this delta V. And if Q is not changing, but if I go from V from 1,000 volts to 10,000 volts, it's very clear that I have done work. I have increased the electrostatic potential energy. And this is what I want to show you. We're going to have that there. So I've changed my...
More voltage with the same number of atoms. So you can't change the number of ions. All you can do is make the ions have more pressure. More or less. you can't change their number. So the voltage is the only thing that can change to increase or decrease the energy of the system.
Television, and I'll have to change the lights a little bit so that you can see that well. So this one off, and all dim. Let's wait for the light to settle, and we want also the current meter. So the one on the right there is the amp meter, the current meter, and you see here these two plates. They are separated now by about 1 millimeter. I have here a very thin sheet transparency which I can move in between to make sure that they don't make contact. And here is my power supply, and I have there this propeller type thing which is some kind of a voltmeter. And if it's going to
some kind, that's kind of funny. Yeah, it'd be nice if you just read it with one of your fancy digital ones, but okay.
Move in this direction, that means that the voltage between the plates increases. And so I'm going to charge it now. There's a potential difference of 1000 volts, and as I do that, you will see a very short surge here on this amp meter. That's not very spectacular, but at least you can see for the first time in your life that charge is actually flowing from my power supply onto the plates. And you will see, psh, and that's it.
First time. I think some of these students have probably seen it before.
It will only be a current as long as the charge is flowing. So let me first do that. Look at the amp meter there. 3, 2, 1, 0. That's all it took to charge this plate. It's now fully charged, 1000 volt difference. And now, as I'm going to increase the gap, there's no reason for any charge to go away from the plate, so the amp meter will do nothing. But you're going to see this propeller, which indicates the potential difference between the plates. You're going to see it move because I'm doing all this work. I'm going from 1 millimeter to 10 millimeters. I'm creating all these electric fields, and this hard work pays off in terms of increasing the potential from 1000 volts.
Right. It's increasing the pressure because now the space the pressure has to occupy is shrinking because there is less attraction between the individual little bits. They're further apart, they're less attracted, therefore they can't create two-dimensional space to exist in. Well, three-dimensional. And so they're collapsing back to the surface, and by collapsing back to the surface, they're pressurizing each other more because they're crowded now.
Volts to 10,000 volts. So there I go.
Remember, the closer the electrons, the more pressure because the more impacts. So the closer the ions get to each other, the more the stuff bounces between them. That means the more they get hit, the more they pressurize.
I'm 2 millimeters now. Look at the voltmeter. There's going. 3 millimeters. I'm doing all this hard work while you're doing nothing. 4 millimeters. I'm creating electric fields. You should be proud of me. I'm creating electric field. Look at that. The electric field remains constant between the plates because the charge is trapped. The charge can't go anywhere. I'm now at 7 millimeters, 7,000 volts.
So this sort of connects to the video a couple of videos ago where he was doing the infinite plane with the little balloon. So you can sort of see that if he used a different surface, instead of the little balloon, he used a flat plate, that the voltage would have increased because he was using two repulsive. He was using a minus and a minus charge, so they're repulsive. So the closer they get, there's an increase in the voltage. So when it's opposite charges, distance makes more. So he could have done this experiment with two opposite charges and pushed them together, and you would have seen the same result. So that's how it compares to the infinite plane argument. But clearly if he had used different surfaces contacting each other, you would have seen the reflective aspect. And the point is that it's the number of reflections that dictate pressure. So if you have like charges, you get lots of reflections. You have dissimilar charges, then you have that idea that the low pressure is created. So the closer you get, more low pressure because everything's just leaving perpendicularly on both sides. And if they're opposite charges, you can see the closer you bring them, the more impacts, the more pressure. So voltage increases with same charges when you move them together, and voltage decreases when you move like charges towards each other. You know, there's a lot that you got to perform this dance in a certain, you know, it's like any kind of orchestration. You have to kind of put these concepts in the right order to get them all kind of in your head the right way. But again, fundamentally, all there is pressure of ions, and their proximity is their pressure. So the closer they are, the more pressurized they are. So you can think of that, they get smaller, you can think of it, or some other kind of thing, the closer they get. They get bigger, you should say. Yes. Closer they get, the bigger, more space they're taking up. But that's all you have. All you have is the number of them that you can fit and how much pressure is between them. So obviously if you make the space they can occupy smaller, their pressure has to go up, because they're going to be like charges on each plate. Even though the two plates are opposite charges, it's the same things happening on both plates. They're getting less, there's less space for them to occupy.
8,000 volts. I mean 9 millimeters, 9,000 volts. Notice that the ammeter does nothing. No charge is flowing to the plates, no charge is flowing from the plates. I'm now at 10 millimeters.
He has no wires connected to the plates, so that's completely unremarkable because they're not connected to anything. They're completely isolated from any conductor, so there shouldn't be anything on the multimeter because it's disconnected. Yeah. Look, the disconnected multimeter reads nothing. Well, of course it reads nothing. It's disconnected.
And now I have created a huge volume, electric field, and the potential difference is 10 times larger than it was before. And so you see that I indeed have done work. You see it here in front of your own eyes.
So what would have made this experiment a little better is if he just put a wire from the two plates and put two little balls next to each other, and he put them in like an inch gap and just kept turning it and turning it and turning it, and eventually he would have gotten to the breakdown voltage between the two little balls, and the spark would have sparked, indicating 10,000 volts. But you know, why should I pick? All right, so I guess we'll end here. It's just good policy to, I mean, I have gone through much of this video, so the other video might be kind of short, but you'd probably like that anyway. So I think we've done enough for this video. It's a good experiment to end on because it demonstrates my principles, I think, very well. So, good from my side. So, till the next time and such. Oh, I really wasn't in the right position. Nothing unusual there, though.